So we have spent the entire semester so far talking about the fact that there are charge carriers in semiconductor material, and we've talked about how to determine how many slots there are for charge carriers and the probability that those slots will be filled. So the only thing we really haven't ever done is figure out how many actual carriers there are, which we are going to do today. First of all, we need to talk for a minute about thermal equilibrium. I may or may not have mentioned it, probably, sort of not, maybe, I don't know. Thermal equilibrium is just the state of something that has no forces acting on it. So there's no voltages, electric fields, magnetic fields, no weird temperatures, temperature gradients, no applied force, nothing like that. Basically, thermal equilibrium means that it is an item sitting on a table doing nothing in a room that has no temperature change. If we're at 300K, it's about a room like this. The 300K is a little warmer than room temperature, but not terribly much. So when we talk about thermal equilibrium, it means that we're going to just have a standard temperature at which we assume the device is at, or at which the device is. So what this means is that if there are no forces acting on semiconductor material, no weird temperatures, no electric fields or whatever, stuff still happens. So in a semiconductor material that's just sitting doing nothing, it's actually doing stuff inside that you can't really be aware of. So they, even though they look static, they're really not, because electrons never stop moving, so they're always going to be moving around, which means holes never stop moving. They're going to be moving around. And we're going to begin to talk about how many electrons and holes there would be in a material, and then what happens when we start to add impurities, which will take a little while to get to. Not all of this will we do today. So first of all, as a review, we talked about the density of states function. This is the thing with all of the, has the h cubed in the bottom, and it's difficult oftentimes to calculate the actual number that comes out, the number of states, but one can do it. And generally for most materials there are, the numbers of states are in the 10 to the 20, 10 to the 21, 10 to the 19, something like that. So there's lots of states available. And remember, we can integrate under the curve and then we find how many states there are. So that's one function that we learned about before the test. The other thing was the Fermi-Dirac function. And that tells us the probability of a state being occupied depending how far above or below this Fermi energy the system is. What we're going to do is we're going to put those two functions together. So in the next slide, you'll see the same density of states function, but the Fermi-Dirac function is going to be pivoted. So where you see it now, the one is on the top, and it's going to pivot this way, 90 degrees. I think it's that way. Let me make sure. 90 degrees and flipped over. So basically, it will look a little different, but you should be able to see it when I go there. So first of all, we've got the density of states function by itself. Then we're going to add the Fermi-Dirac function. So you see how it has been turned kind of on its side and flipped over, but that's still the basic thing. And the Fermi energy is where it reaches its midpoint, where the probability is 1/2 that a state would be occupied. So when we put these together, we can multiply the functions together. And when we do that, we get this little bulge out in the end. So that's basically just taking the two functions, multiplying them together, and putting what that function looks like kind of on the outside. And you'll notice it's just the two functions multiplied together. And we can do the same thing with the holes. This time we have to use 1 minus the Fermi-Dirac function because we're at kind of the other end of the function. But in both cases, we get kind of an area, and inside that area, if we take that curve that's made by multiplying the two functions together, we can actually find the concentration of electrons and holes. So that's the process that's used. There is the density of states function, it's multiplied by the Fermi-Dirac function, and then it's integrated to find the number of electrons or holes. The good news is you mostly don't have to do a lot of math. We're going to do a lot of math to get to a certain point, and then once you get to the point, it's going to be a lot easier. So there's a lot of constants that are going to be bunched together into kind of one, and then because you've got a lot of constants bunched together and known substances, somebody has already gone out and figured out what all these constants come out to be at a certain temperature. So don't worry overly much. So just zooming in on each one of these areas that have concentrations, if we look at the area for the number of electrons, you basically see there's just a kind of a big funky looking curve, and the area underneath that is going to be the number of electrons, and the same with the number of holes. We have the area, and the area underneath it is going to be the number of holes. So that's just kind of the zoomed in version of what we were just looking at. We're going to talk about intrinsic semiconductor material. Pure, no impurity atoms, no lattice defects, and at zero, absolute zero, all the energy states in the valence band are filled and all the energy states in the conduction band are empty. So that's the condition at 0 K. As you add thermal energy, as semiconductor material heats up, electrons and holes are created in pairs, because every time an electron gets enough energy to move into the conduction band, it leaves a hole behind. So they're always created in pairs in intrinsic material, which means they're the same number of them. And we can just say that the number of intrinsic electrons equals the number of intrinsic holes. So little n in this class is always going to be the number of electrons. Little p is always going to be the number of holes. And then the sub might mean something, might not. But a sub I means intrinsic. So that's what's in intrinsic material. And the Fermi energy is near the middle of the band gap between the conduction and the valence energy. So it's close to the middle. It's actually not exactly in the middle, but it's close. So if we want to find how many electrons there are in the conduction band, we have to multiply the two functions together, and then we have to integrate from the conduction energy up, because that's basically where all the free electrons would be. They would either have an energy at the conduction level or an energy greater than that. So that's basically how we're going to have to figure that out. We assume the Fermi energy is near the middle of the band gap, so that means we can use the approximation formula we talked about briefly at the end of talking about the Fermi-Dirac function, where we take the 1 over 1 plus away and we just use the exponential. And we can do that because the difference between the energy and the Fermi energy is going to be a lot greater than the Boltzmann's constant times the temperature. So we're going to use an approximation formula, which is going to make this easy. Not easy, just easier. Do not get worried. I am going to derive how we get from point A to point Z, but once we get to point Z, you can just use what I got, and you just need to know where it comes from. So it's not some equations I give you and they just seem to come out of thin air, and that's fine because I don't care to explain them, but I am going to explain where this comes from so that you know. So we have this integral of two functions, and the two functions are going to be given as such. The density of states function you've seen before, you've used it before, and then it's just multiplied by E minus EC. And we use square root. I do it to the 1/2 just because it's easier to deal with. And then the Fermi-Dirac function, we use the approximation version, where we take the exponential of minus E minus EF over KT. All right, so the first thing we have to do is multiply those two functions together, which is going to make a little bit of a mess. So we're going to put them all up there like that and take the integral of that. In order to make the integration easier, we're actually going to change the variable of integration, which I haven't done in forever and ever and ever. I don't know how often you guys have done this, but I forgot how to do it, and I had to go back and look it up when I first did this. So, but basically, we just take a new variable and we equate it to something messy. And then we take the derivative of the messy thing, and then we get, the d whatever, to figure that out, to put that in the integration. So we're going to use eta, and that's going to be equal to E minus the conduction energy over KT. And that means that d eta is going to be 1 over KT dE, but I want dE because I want to replace that in the formula, so that's why I have it listed that way. That was the thing when I first did this for the first time. I forgot that you have to change d eta to something, and there was an extra KT and I couldn't figure out where it came from, and that's why. So now I know. Anyway, so we're going to go ahead and substitute in this new variable, and when we do that, we get E minus EC to the 1/2 is going to be equal to eta to the 1/2 KT to the 1/2. Which means we take E minus EF over KT, and that's going to be minus E plus EF. I'm looking at like two different slides at once. There we go. That has all that mess, E minus EF minus EC plus EC over KT. And that means that we can kind of, basically what I did was I added minus EC plus EC. So that was added by me. I can do that because it's mathematically equal. And I need to get this into a form that's actually usable. So that means I can split that fraction up into two fractions. One is minus E minus EC over KT, and one is minus EC minus EF over KT. And the minus E minus EC over KT is the new variable eta. So we now have minus eta plus minus EC minus EF over KT. So far, so good? Maybe. So we put that into our equation. And I keep the stuff at the top so that you can remember what it was that I did. So all I did right now was the stuff at the bottom of the last slide kind of got shoved up to the top of the next slide. So a lot of it's still there. This is just so I can keep going. And when you go through and do this whole thing, a whole bunch of this is constants, which means I'm going to take pretty much every constant and put it outside the integral. And that's going to be almost everything. Not quite everything, but almost everything. So the exponential is outside of the integral. The constants that we had before are outside. KT to the 3/2 is the outside. And the only thing that gets integrated is eta to the 1/2, and then we have the exponential minus eta d eta. So that's what we end up with. The cool thing about this integral, this is an integral for which the answer is already known, and the answer is actually a constant. This is something called the gamma function. And the solution to that is in every integral table or every book or whatever, and it equals the square root of pi over 2. So that integral part actually just becomes another constant, which means the only thing that actually has values that we don't know is kind of the conduction energy and the Fermi energy, which we kind of sort of even know that. So we're going to take this whole mess and kind of put it together. This is what we've got now after doing the integration. We still have a big mess, but it's a better mess than it was before. So we can actually simplify that whole mass of fractions and exponents and pi's and k's and t's. And if we do that, we get 2 pi to the 3/2, 2 mass, effective mass to the 3/2, kt to the 3/2, which means we're going to be able to put all those together, over h cubed. And so we can take all that stuff to the 3/2 and put it together. We're almost done. We can take h to the minus 3, because that's the one weird thing that we need to do something with. And that's equal to h to the minus 2 to the 3/2, if that makes sense. So I can put that inside as well. And what we end up with is 2 times the effective mass times pi times kt over h squared to the 3/2. And that actually has a name, because other than temperature, there is nothing in there that varies as long as you're using a particular material. The effective mass of the electron is going to be different if you've got silicon or germanium or gallium arsenide, but the temperature also is going to be different, but you can standardize this. So we give this a name, and we call it the effective density of states function in the conduction band that varies with temperature and semiconductor material. And this means, because this is something that just varies with temperature and semiconductor material, that someone has already figured out the value of this. And there's actually a table for these values, which I'll get to in a minute, that gives you the values of N sub C for silicon and germanium and gallium arsenide at 300K. So those values, all that mess, is just down to one constant, and that constant can be looked up. So that makes it a little easier. So when we finally get through all this integration, what we end up with is the thermal equilibrium electron concentration is equal to this N sub C, which we can look up, times the exponential of minus EF over KT, which we still can't quite find, but that's okay, we'll get to that. So that gives us the number of electrons. What this means is that if we know how far the Fermi energy is from the conduction band, if we know the difference between the two, we can easily find the number of electrons. If the Fermi energy is 0.2 electron volts above the conduction energy, we can figure out exactly how many electrons we have. If the Fermi energy is above the the conduction energy, that means there's a lot of electrons. Actually, it means that there are way, way more electrons than need be. And that is, there is a type of semiconductor that does that. But so as long as you know the difference between the Fermi energy and the conduction energy, you can figure out how many electrons there are. And the more electrons there are, the more the Fermi energy moves up towards the conduction band. So we'll look at a short example, not a long one, but if we have the Fermi energy being 0.2 electron volts below the conduction energy, which makes more sense, and we have a value of N sub C at 300K, we can calculate the thermal equilibrium electron concentration for this particular material. All we need is to take N sub C, which we were given, and do the exponential function of minus EC minus EF over KT. And remember that I have to get KT into electron volts, so I'm actually use KT over Q, and at 300K, it's 0.0259 electron volts. That's actually, we've calculated that value before. So at 300K, that is that value. It's not the value at other temperatures, but at 300K, that's the value. So we can take 2.8 times 10 to the 19, and then do the exponential function on minus 0.2 electron volts divided by 0.0259 electron volts, and we get 1.24 times 10 to the 16 per cubic centimeter. And that is how many electrons are in a cubic centimeter of that material. And that's a pretty good, it's pretty amazing that we can even figure that out if you think about it, because that's a lot of electrons in a very small space, and that's probably not exactly the number that there are, but it's pretty close. And that will make a difference when we start dealing with semiconductor materials in general. We do need to know how many electrons and holes there are. The good news that when I talk about hole concentration, excuse me, I'm not going to go do that whole derivation again because it's the same one. So all I'm going to do is tell you how they're different, and then tell you what the answer is. So this is exactly pretty much the same thing that we looked at a minute ago. The only difference is we integrate from minus infinity to the valence energy versus conduction energy up, because holes reside in the valence energy band, and the highest energy that they can get is the valence energy. They're going to be there or lower. So we go from negative infinity to the valence energy, and the results are almost exactly the same. The only difference is we now have an effective density of states function in the valence band, which is material and temperature dependent. It has already been figured out for 3 different materials at 300 K, so that's tabulated as well. And we take the Fermi energy minus the valence energy, because the Fermi energy is going to be above the valence energy in this respect. So if we are 0.25 electron volts above the valence band energy, we can find how many holes there are, and this time we're going to find it at 350 K. We only have tabulated, there's got to be a tabulated, there we go, tabulated values for 300 K. So we have to adjust the values that we have. So the value of N sub V varies with temperature to the 3/2. So in order to adjust this for temperature, we're basically going to take 1.04 times 10 to the 19, and then we're going to multiply by the new temperature over the old temperature to the 3/2, because basically I could go back to the original constants and do the whole thing again and just plug in 350, but you don't have to. You can just know that they're related by temperature to the 3/2 and just adjust it accordingly. And when we do that, the new value we get is 1.31 times 10 to the 19 per cubic centimeter. And also, we have to adjust the value of KT over Q. I could go and calculate KT over Q if I wanted to, but I can just take the value that we got in the last problem, 0.0259, and then just multiply by 350 over 300, and that will scale it up to the value that we need, 0.0302 electron volts. You can do that with KT over Q for any temperature, rather than using Boltzmann's constant, multiplying by the temperature and dividing by the electron concentration. You can just use 0.0259, which is the value at 300, and just scale it up or down by putting the new temperature on top of 300, and that will either make it lower or higher depending on what you're doing. It's somewhat easier than calculating it all out. So this means that the number of holes is going to be the density of states value times the exponential minus EF minus EC over KT. And remember, that's really KT over Q to put it in electron volts. And we get 1.31 times 10 to the 19 times the exponential of minus 0.25 over 0.0302. And we get 3.33 times 10 to the 15 per cubic centimeter. Most of the time, your electron or hole concentrations will come out to be large numbers. But when we get to the point where they're unequal, you may come up with some that are really small because the others are really large. But for right now, whatever we calculate in intrinsic material, the two values are going to be the same. They're always going to have the same number of electrons and holes. So there is a table like this, either in the book or online. I do provide these tables for you on D2L, so if you don't have the book, you don't have to go look for the tables. But this basically tells you the values of the effective density of states at 300 K, and then if you're going to adjust it for another temperature, you just basically take the new temperature over 300. Just remember, it's to the 3/2 when you're dealing with this value. So you can have this table, and there's also one that gives you the effective mass for different materials and different values. And we've talked about effective mass before. I'm just pointing out again that you can look this stuff up because we will need to talk about it later when we talk about Fermi energy and where it's located. So that is another thing that you have at your disposal. So going from there, since we create electrons and holes in pairs in any material, oftentimes in intrinsic material we just use the electron concentration to talk about how many carriers there are because the electrons and holes are going to be equal. So usually we talk about N sub I in intrinsic material. We're referring to electrons or holes because the hole number is exactly the same as the electron number. So basically this means that if we take the number of intrinsic electrons and number of intrinsic holes, we can calculate them using the values that we just did. But if we multiply these two things together, we can find the total number of carriers in the intrinsic material based on just temperature. So since you're going to have to multiply the two together to get the total, we can do that. We can actually multiply these two together. And what we end up happening, we get Ni squared, which is just the number of electrons times the number of holes, which means we can take those two equations that we had and just slap them together. And remember, when you put exponential functions together, that means you're adding together everything inside the parentheses. So NC and NV end up being multiplied together, and then inside the exponential you have this whole big long thing, but you will notice that you have plus the Fermi energy and minus the Fermi energy, which means we can take those and just get rid of them. And we get NC, NV, which we can look up, and the exponential of minus the conduction energy minus the valence energy over KT. And that already has a value. That difference between the conduction and the valence energy, that's the band gap energy. That's something we can again look up on a table. It's the distance between the top and the bottom. So we can actually, when we have the band gap energy between the two, we can just substitute that into that equation, and that gives us the square of the number of intrinsic carriers in any material. And for any material, the band gap energy is already known. That's also tabulated. There's this wonderful appendix in the back of the book called Appendix B, and then within it, it has a table that has all these different parameters for semiconductor materials. And band gap distance or band gap energy is just one of those things. You can go look it up. So since the number of intrinsic carriers can be found using all constants, we can find the number of intrinsic carriers in silicon or gallium arsenide or germanium without having to calculate it every time, because somebody has already figured this out. So somebody already took these materials and calculated how many carriers you expect. Once you go through this process and you figure out Ni squared, if you just take the square root, then you can get the number of electrons and you assume the number of holes is the same. So there's actually a table, again, that gives us the expected number of carriers in intrinsic material. And this is just for electrons, but holes will be the same. And you'll notice that in silicon, it's 1.5 times 10 to the 10. That's how many electrons we expect in a cubic centimeter of silicon at 300 K just sitting there. And the same goes for the number of holes. Number of holes can be equal. You'll notice that gallium arsenide has several orders of magnitude less electrons available because of the type of the material it is. Germanium has more because of the type of material. So it's material dependent, but it's relatively easy now to go look up how many intrinsic carriers we need. And that's going to become important later. Today it's not going to be as important, but later it will actually be important when we start to calculate numbers of electrons and holes that aren't equal. So in intrinsic material today, they're going to be equal, but then later next week, they're not going to be equal. So we're going to have to do something with that. So we're going to calculate the number of intrinsic carriers in silicon at 350, and both N sub C and N sub V will vary with temperature. This is a slightly different temperature. So what this means, first of all, that KT over Q is again going to be different. So I'm going to take 0.0259 and multiply it by 350 over 300, which we just did a second ago. So we're going to get the same temperature we did, but I know students have short memories. So there's that number again. That's where it came from. And then we're going to take Ni squared as NCNV minus Eg over KT over Q. And that means I'm going to take the two values that were given before, and I'm writing these down because I know what they are from the table, and we did this in the previous problem. And then I have to adjust both of these for temperature. And when I do that, they each vary by T over 2. So in other words, they vary by T over 3/2. So if I put 350 over 300 to the 3/2 twice, that's just like putting it cubed once, because to the 3/2 times to the 3/2 is just going to be cubed. So I'm just going to leave it cubed. And then we take the exponential of the band gap energy, minus 1.12, over the temperature, which is 0.302. And we get Ni squared is 3.62 times 10 to the 22 per cubic centimeter. So we take the square root and we get the number of intrinsic electrons at 350 to be 1.9 times 10 to the 11 per cubic centimeter. So there are more than there would be at 300, which is good because that's what we would expect. We would expect more carriers at a higher temperature. Last topic. We're going to talk about the Fermi level in intrinsic material. Remember, the Fermi level is basically telling you the highest energy level in the system, whatever that may be. You would assume that if the carrier numbers are equal, and you have an equal number of electrons and holes, that the Fermi energy would be in the exact middle of the band gap. That would just be the expected thing. And that's almost what's actually going on. It's not quite, but almost. It is close to midway between the two. It's not usually exactly midway. And the reason it's not exactly there is because it depends on the effective masses of the holes and the electrons. And remember, effective masses of holes are different than the effective masses of the electrons. So the difference between the intrinsic Fermi energy and the mid-gap, which is exactly halfway, is equal to 3/4 kT times the natural log of the ratio of the effective masses, meaning that we don't really need to use the actual mass, because the actual mass is going to cancel in the numerator and the denominator, so we can just use the ratios. So what this means is if the two effective masses are equal, which they really aren't ever, then the Fermi energy would be exactly in the middle. If the effective mass of the holes is greater than the effective mass of the electrons, then the Fermi energy moves up just slightly. And this is like an over-exaggeration of the amount that it moves up. The amount that moves up is really, really, really small. If the effective mass of the holes is less than the effective mass of the electrons, then the Fermi level is slightly below that. So it's really, really, really close to the middle, but it's not exactly at the middle, depending on material. So as a last example for the day, we're going to figure out the position of the intrinsic Fermi level with respect to the center of the band gap, because anytime we find a Fermi level, it's always got to be with respect to something. So it's going to be with respect to mid-gap or intrinsic Fermi level or whatever. So we have the effective mass of both the electron and the hole, and we're just going to figure out what that is. So the intrinsic value minus the mid-gap value is going to be 3/4 times kT times the natural log of the two effective masses, MP star over MN star. And remember that this is really like KT over Q, because it's going to have to be in electron volts, again, because the difference between energies is going to be in electron volts. And we're at 300K, so we can use that value of 0.0259. We don't have to calculate that again. So the difference between the two is 3/4 times 0.0259 times the natural log of 0.56 over 1.08, which equals minus 12.8 milli electron volts. So it means the Fermi energy is like 12.8 milli electron volts below the mid-gap, just slightly below. Not much, just a little bit. That's all I have for today. Next time we're going to talk about what happens when we add impurities, because intrinsic silicon really doesn't do anything. It just sits there. Things move around and things get created, but that's it.